Welcome to EE 569 on Friday, October 15, 2013.
So the PowerPoint will be, I think the PowerPoint is already posted or no? From last week, it's already posted. Okay, so that's about color image processing. So today we will continue the lecture on the geometrical modification. Okay, particularly talk about the camera image modeling. Hopefully, we also have time to talk about texture classification and segmentation, so that we are able to finish everything you need to do the homework number 3. And we will have the midterm in 2 weeks, so it's the next week during the class hours. It's an open book exam. So basically, you can bring whatever you have. And also, in terms of the computing device, you can have the calculator, so one-line calculator. That means you cannot program there. But it doesn't matter. You really want to program, you don't have time. Okay, so, but anyway, I think just to be fair for everyone, we make the rule clear. So basically, it's a line computer, a line calculator, so that you just do the simple arithmetics. Some students worry about the midterm. We will give the sample midterm from previous semester, so that you can know what's the flavor. But basically, as long as you do the homework yourself, you shouldn't worry too much. So the flavor is like homework. But it's ask you something. So if you do the homework, you think about that, then there is no programming, of course, in the midterm, but it's more like a test your concept, your understanding of the subject. It's open book, so I don't know how much you really need to prepare. You know, when there is a closed book exam, you may have to memorize many things. But if open book, basically, is really see whether you know the material or not. That's the key. You don't know the material, 3 hours will not be sufficient. Right? But if you know the material, you should be able to do a good job. So we'll give you the sample exam so you know the flavor, what it will look like. And the homework number 3 will be due the Sunday. And the reason for that is the midterm will cover everything up to homework number 3. Okay, so whatever up to the texture, segmentation, let me write down. This is very important information. So the midterm will be the, it's 11 first? 11 first. Today it's 17, right? And 17, that's the 31st. Yeah. Is this right? No, it's November 1st. And today is the 18th? And so last time I made a mistake. It should be, so this should be the 4th. So I made a mistake. So everything made a mistake. So this is not 3rd, it's 4th. And this is 18. Okay, so it's from 9 to 12, just during the class hours. Room we need to find out. Okay, we'll announce the room. So usually we put the TBA, means to be announced. Okay. To be announced. So the scope, the coverage is basically the material in homework number 1, number 2, and the number 3. So these are 3 homework problems will be the coverage of the midterm. And homework number 3, of course, also due on the November 3rd, Sunday. I got the feedback from some students. They say, well, can we postpone the homework number 3? The answer is no. The reason is very simple. You postpone, many students will not be able to study homework number 3. You know, there's always human nature. So you postpone 1 week, then you don't study. You don't study, how you can take the midterm, right? Then some students say, well, can we postpone the midterm? Midterm cannot be postponed. That's a day 1. We set the midterm day. This is a 10 class, then the distance education system. Everywhere sync with this midterm exam date. So we cannot postpone, okay? And the reason I want to pick that particular week, because I will be out of town to attend a conference in Asia. So I will be away in that week. And next week I will be here. So sorry, I cannot change that either. So you just have to do the homework. And when you prepare exam, really it's your regular preparation. You don't need to do anything special for the exam. Okay, so these are the 2 things in 2 weeks you have to pay attention. So we'll give the sample exam from previous year. I think why not let's give 2 years, okay, the TA will, so let's give 2 years previous exam. So the fall 2012 and fall 2011, 2 years. I think there's no solution, okay, you just have to do it yourself. So but it give you the flavor, what kind of problem being tested there. So from these 2 semesters, then you can see, okay. Anything you want to know? Again, I have to say that you start homework earlier. You know, I hope you already start, and if not, you have to start tomorrow or tonight. because it's again, it's just a lot of things you need to learn and so on. Okay, so so let me go over the homework 3. The problem 1, I mentioned before, I want to do a little bit here. Again, so this is the first one. I already went over it, but let me just go a little bit more. So again, as I said, you have to consider triangle. Okay, so consider the triangle and the generalized affine transform. You know what I mean, generalized transform. Have you forgot or you still remember? This is a generalized affine transform. It's a first order, so it's there is a output and there is an input. Okay, so this is the coordinate of the output image and the coordinate of input image. You can through this transformation, and then you have the UV, you have the JK. Let me see. So you have the U1, V1, U2, V2, U3, V3, and you can go to the U1, V1, go to J1, K1, that output, and the 2, UV, U2, V2, go to J2, K2, and so on. But you want to write the reverse form is look at the integer JK and find the corresponding UV. But UV may not be integer. UV may be fractional number. But then you have the bilinear interpolation. You are able to compute the gray label at this point. Okay? So the whole algorithm basically says from the output coordinate, you find the corresponding input coordinate, and then find its gray label or color, right? Gray label color, and then get that gray label color copy to the output. Okay? If they happen to be integer location, integer UV, you are lucky. Usually you will not be integer. Usually it will be fractional. The fractional, it doesn't matter. As long as you have 4 near integer, this 4 near integer will do you can perform bilinear interpolation to find the value, the either RGB value or the Y value of that point, and then calculate that and copy that. Okay? So it's really about the image coordinate transformation. And then using that that's the input image coordinate, find the corresponding height. Height means color or gray label, and then copy. Okay, and so triangle. If you want to transform a triangle from one to the other, you just need. These are the 3 key points. We can call this like leaders. So these 3 key points define how this triangle go to that triangle, and then you need so you have 6 equations. So this one go to this one, you have 2 equations, and this, so totally you have 3 vertices, each one 2 equations, so totally you have 6 equations. And these 6 equations, it's sufficient to determine these six parameters. And this just augmented, right? This just augmented. Because the formula you are looking is we define an augment system. Let me show you. We put a 1 in the Z coordinate.
The time is 0 o'clock.
So 1, 1, 1, 1, 1, 1. But the reason we put a 1 here is to make the translation easier to take care. You know what I mean? We put a 1 here. The last equation is dummy. It really has no purpose. But this is very convenient because you are able to handle the translation. Okay, so so eventually you can write down this way. This way is like a forward transform, but you can do the inverse transform as well. It doesn't matter which way. You can put the input image here, output image here, but you can reverse all the output image here, output image coordinate here, input image coordinate here. Okay, and then just find these 6 parameters. These 6 parameters, once you determine that, then you can find all others. Okay, so so the key is to find the triangles. And so now let's come back to the computer screen. So if you see this, it seems like very hard to find triangle. Actually, I can tell you the secret, okay? The secret here is not consider 4, rather than consider 8. So it means we divide this quarter by another line here, so it's become this part and this part. So it's 8 pieces, but each one is a triangle. So there's a triangle here, there's a triangle here. And this triangle will go to what? Go to this triangle. And this upper triangle go to this part. Okay? And then now you can see the 8 corresponding triangles, right? And that's it. So as long as you do this 8 times, and then you don't need to find the vertex here. It should be easy, right? The vertex here and also the vertex here. And once you use the 3 vertices and these 3 vertices, you find the 6 parameters, then you can bring the whole thing to here. And similarly the other, just repeat it. You have to write a subroutine, just using the, you can allow the input here. You just, a triangle transformation. The input will be operate. Can you show the notepad? Here. So you need to write a subroutine, try to relate this. You can allow the user input this, and so on. And make it just a subroutine. And you call it, you just choose the one you like. Right? You choose the pair you like, and then you just as an input. And then it will automatically compute everything for you. Is that easy? Actually, I sort of teach you step by step, like more like a kindergarten professor or kindergarten teacher. It's all the detailed steps. So, you know, I think there are smart students, but there are also some students need a lot of help. So I try to Okay, so again, look at this one. Looks like a very fancy one, but remember just triangleize. So you look at this and then see the triangle space. I think the middle is here. The middle is here, right? And then you look at, you need 5 triangles at least, right? 5 triangles. And how to find the 5 triangles here? Then I think you can recognize that it's one triangle will be here, right? And then another triangle. It seems to be, I think we can cut this into this part. How to divide the proper triangle. This one. We need to divide it into 5, okay? So this one, yeah, you can choose this guy, right? So this bigger one become the smaller one, the base being shrinked. Okay, so this is correspond to this one. Then this one, you need to go to the ear. You need to go to like a, but I think there must be, it must be go here, I believe. And yeah, because it's squeezed. This one you cannot see much. But I believe this will be this part, will be correspond to this part. Okay? And this part will correspond to this part. And finally, these two, you just split. One here, one here. That's my observation, okay? There's no guarantee it's definitely correct, but at least give you some hint, you try it. So my suggestion or my thinking will be, you need 5 triangles. So this will be one, this will be another one, the third one, but the middle one you split and then become 4, 5. Have anyone tried this? Or you haven't started? You will do it this week. This one. So this one basically, you have to use the polar coordinate. So you have all the points, you measure the polar coordinates, and then you come to this. So this is a polar. It's easier to describe polar coordinates, and look at the fixed theta, and you see how r change. So there is a different r change. The radius will change according to theta. For example, theta equals 0. This is 1 to 1. R is 1 to 1. Okay. Theta equals 90 degrees. R also 1 to 1. This R and this R 1 to 1. But if theta equals 45, definitely is not 1 to 1. It's like 1 over square root of 2, right? But in different location, different theta is a different ratio. So you just have to do that, and so on. And then the rest is just the reflection or whatever you can do. Any question about this? Actually, I made it very simple so that you don't have to think much. And so these are the example, but actually you are going to apply to these images. Okay, so apply the diamond for this guy, for puppy, and you apply the star, the pentagon shape for this cowboy, and the circular one for this like transformers. Okay? So you don't know the result. Okay? So you need to apply. You don't know final result. This result just show you the desired input-output. But eventually you apply to this 3 and see the final result. Any questions about this? Okay, now let's go to the homework number 2, problem 2 in the homework number 3, so-called perspective projection and imaging geometry. So this problem, basically, it's one of the very basic exercise in computer graphics. So computer graphics, basically, there is a 3D world space, 3D coordinates, world coordinates. And usually we use the capital X, Y, Z to denote the 3D world coordinates. So it's a 3D world. But when you see cartoon, or you see computer graphic cartoon, okay, not the traditional hand drawing, it's a new type of cartoon in the computer graphic generate. You have a camera. This camera just like the screen. Whatever showing the screen is a camera. This camera can fly. Okay, this camera can say following some trajectory, doing different translation, can look at the object from different angle. The camera itself can pan, can tilt, can look at different side of the world. Okay, so the surface normal can adjust. And also the occasional camera can adjust. So I give you a very flexible way to see the 3D world. Okay? And the image you see is a project on this image. This is called the image plane. So this is called the image plane. Okay, so this is being used daily in computer graphics. And so now usually we use small x and small y to denote what you see here. So we put the image coordinates, image plane, and the image plane coordinates. And this is the real world coordinates. And we need to relate this to that. Okay. And usually it's we have the focal length. So there's the length here, and there's the length center. And so if you have the parallel light going through the center, then they will passing through the focal point. Okay, the parallel light will go passing through the lens, will go to the focal point, and then project it to the image plane. Project to the image plane. Okay, and this lens and this lens is the same. So this is all the focal length, and so on. Okay, so so we will describe how the things, write the formula, how we transform the world coordinate to the 2D image coordinates. Okay, and so basically, let me write down the things. We will follow. Let me explain the transformation. Actually, let me see. So can we show the notepad? Let's come back to the notepad. So this is which chapter? Do you know the chapter number? I don't even remember. It's a 5 or what? 5.3, 5.2 or 5.3? 5.2? Okay. So perspective. So we talk about the perspective projection and the camera image model. Perspective projection, versus the we call the orthogonal projection. So there are two projections. One so-called orthogonal projection. One is called perspective projection. Orthogonal projection is an approximation of the perspective projection. That means the object distance is much, much greater than the focal length. So the object distance is much, much greater than the focal length. Then we call this the orthogonal projection. So we don't have to worry about the effect of the focal length. Okay, so in that case, we can assume that it's a parallel light, then just parallel light project to the image plane. But perspective is the object distance. Object distance is about the same order as the focal length. They are not too far. Okay? They are close by object. Then you need to consider the effect of the focal length. And so most computer animation, we need to use the perspective projection. So the object actually close. And you can start to see the depth effect. Okay. But orthogonal projection, basically you cannot see the depth. It's just very far. And then it seems to you just a 2D world. It's not 3D world. Okay? So just you take a picture, focal length, put the infinity, very far. It's like a 2D plane. Like photo, but there's no depth. But if you use something close, then you have the depth effect because the focal length play a role. Okay. So usually we have the following notation. We use the XYZ to denote the world coordinate. And using the XY to denote the projected still you project Cartesian coordinate. In the image plane. Then we have we need to consider two effects. One is assume the XY, they are aligned. Let me see. So one situation is a very simple case. In this case, we assume the image coordinates and the Cartesian coordinates, the capital X and X, they are aligned. Capital Y and Y aligned. Okay? And then there is a focal length, and there is the object here. And so this object, X, Y, Z, they will go through the F and then projected a point in the image plane, small x, small y. So this is the relationship between the capital X, Y, Z and the relationship with the small x, small y. This we call the intrinsic mapping. So that means we make some alignment. So the image plane and the 3D coordinate just happen to be very simple configuration. Okay. So under this scenario, we can define a relationship, and that define the intrinsic one. And then there's another one. It's called the extrinsic one, and then it describes the camera start to move away from the origin. Okay, and the camera may has a different kind of surface normal. It's normal in the z direction. Usually we call the x, y is the plane and z is the depth. Okay, so when they are aligned, we call this just z the depth, and this is just the intrinsic model. But then generally the camera image plane can move away from the world coordinate as shown in the figure in the homework. The homework, the camera already moved away. So 3D coordinate and the camera coordinate not aligned. Okay, so that's called the intrinsic. So let me come back to the computer screen. Operator, can you show the computer screen? Computer screen. Okay. So this is a relationship between the image plane coordinates. Okay, image plane, there's x, y, and this is a 3D coordinate. And this 3D coordinate relate to the image plane by two matrices. Okay, this is one matrix, this is another matrix. And this matrix is called the extrinsic camera matrix. And this K is called the intrinsic. So K basically just try to describe after X, Y aligned, capital X, capital Y aligned with small x, small y. They are aligned. The relationship only play a role at F and also CX, CY. Why is CF, CY? CX, CY means translation. So the center can be translated, not more in the same. And F is the focal length effect. So intrinsic actually is quite simple. Just this equation, this matrix. Extrinsic looks a little bit complicated, but actually it's also not very complicated. This relates to translation. Tx, Ty, Tz is the translation effect. R, this matrix relates to the rotation effect. So if you think about it, if you want to align the camera with the origin of the world, what you need to do is you need to first translate the center of the camera to the origin, and which is governed by the Tx, Ty, Tz. And later on, you need to rotate the camera so that eventually the normal, surface normal, image plane there is surface normal, a normal direction. Normal has to be aligned with the z. That's a rotation, and that's this part. Okay, so this is about camera movement, camera orientation, and camera translation. And this just to say everything aligned, x, y all aligned. Only need to worry about the relationship of the depths. That's a simple. So this is a simple way to do this. In the textbook, only derive this guy. The textbook, you can know this part. Of course, it's just they assume student can do yourself. Okay, but in order to make the things complete, we should put both. So the camera movement, and then talk about the focal length, perspective projection. Okay, so this is a better, I think to the TA and so on. So find the other material from the computer graphic textbook. So I feel this approach is cleaner. So we just say the equation 1. Equation 1 we basically have in the homework number 3, okay? So we have the omega xy1 equal so this is we denote by K, this we denote by R and the T. R is a rotation, T is a translation, and we put them together with this kind of weird notation, but basically it's a one matrix, okay? It's a one matrix, it's a 3 by 4 matrix, considering rotation and translation. Okay, so you can say the first 3 columns is rotation part. The T is the last column, is the translation part. So this is about 3 by 4, but this is 3 by 3 and 3 by 1. Okay, so this is a 3 by 4 matrix, and this part I can separate here. Okay, so anyway, so there's the R part, there's the T part, and that's called the extrinsic camera matrix. And so this governing the camera movement. Okay, and this is called the intrinsic camera model, camera matrix. Okay. So let's see how we handle this. Okay, so we can think about the first stage. It's called the extrinsic camera matrix. So can we switch back to the computer screen? So here, this is the first one. Okay, extrinsic camera matrix. From the world coordinate to the camera coordinate. Basically, we want alignment. We want to align the world coordinate with my camera coordinate. Or I can align my camera coordinate with the world coordinate. Doesn't matter. I just want to align origin, meant origin. X, Y, small x, small y, align with big X, big Y. Okay, that's the whole thing I want. I want to make sure the origin the same and X, Y aligned. And how can I achieve that? So here, we can say, well, there's a world origin, there's a camera origin, and the translational effect by this vector R, right? This R is a vector, and then there is a XYZ here, and there's a XYZ of the camera. So we put a XC, C is the camera, so XC, YC, ZC. And the important thing is the X should be looked at, X and Y should be aligned. And these should be also aligned, right? Z, we also want to align because they are just according to this. Operator, can you show the notepad again? So I need your more collaboration today, okay? The switch here backward. So X, Y aligned, origin aligned, but Z actually, there is a camera coordinate. There is another Z here. So there's an image normal. There's image plane. There's a normal of the image plane. And there's a real world Z, right? There's a real world X, Y, Z. And there's a surface normal. This one also aligned with the Z. Is that clear? So not only X, Y align well, Z had to be aligned. Okay. So now switch back to the computer screen. So how we write this, okay? By looking at all this, can you find it's like this? Can you just write it using your inspection? By inspection, we get this. Usually when you read the paper, then people will say, by inspection, we get blah, blah, blah. This. And what's this XC, Y, this is these are XC, right? This is a vector, and the XC is written as this line. And YC is here, and ZC is here, right? And then the R project to the XC, R times this XC, and this R, this is the inner product. These are the vector inner product, and RZC inner product. So this translation. So just say by inspection you get this. But usually when I was a student, I say by inspection I took like 2 hours, 3 hours to understand what's going on here. So can you see by inspection you should get this? Well, this is really not that difficult, okay? So what I want to say is, number one, you need a translation, right? So you need this guy translation back to this guy. And so you need to find the translation amount. So how much you need to translate in X, how much you need to translate in Y, how much you need to translate in Z. Isn't it the inner product of this guy and this guy? This is a unit vector, okay? This is the unit vector. So XC are the unit vector of the camera coordinate with respect to the world coordinates, right? So this is we use the world coordinate as the main thing, and the camera unit vector, I call this XC, soup, X soup, Y soup, Z, means the XYZ component, right? 3D. So this time this will be the projection of this along the X direction, projection of this along Y direction, projection of this along the Z direction. And through this kind of translation, you are able to move here back to here. Do you agree? If you have any problem, go back to 2D examples. 2D example tell you need minus TX, minus TY, those kind of things. (2D) translation. Operate, show the notepad. If you have a this is examples, okay. Let me show you. If you do forward translation, then the forward translation will be plus, then you can write down TX, TY like that, forward translation. And the inverse translation will be minus. So this is forward translation. Okay, forward translation will be this guy move to the TX, to the TY. So if your world coordinate here, you move forward to that direction, it's plus. But reverse direction will be minus. Okay, so this is just like the case. So that's about the vector t. This is the vector t here. How about this? This one, it depends on how you think about the angle. So when we have a matrix, you can have two ways to look at this matrix. So suppose we look at a rotational matrix. It's 3 by 3. If you do this way, it's a you basically try to look at the camera coordinates, project to through the rotation, and what's the world coordinates, right? So this is XC. How to say? This really is the unit for how much XC you have. So basically, we should say this: it's what I would like to say is okay. You have two ways to look at the rotation. So one way to look at the rotation is try to look at the rotation of X. It's a vector, so it's a unit vector. It's a 1, 0, 0. Y, it's a 0, 1, 0. Z, 0, 0, 1. Through this rotation, project to the XC, YC, and ZC. and this is their corresponding. They are defined in the plate, right? This is like SCX, XCY, XCZ, right? So you can look at this. It's a rotation this way, but you can also look at rotation the other way, right? But this really is about the change of the coordinates, okay? Really about the change of coordinates. So the easiest way to look at this, and if you want to do the forward, you should write down this as this row vector times R give you the corresponding row vector. So this is a row vector. It's a forward direction. And if you want to look at the backward direction, you'll be look at the column. So there are two ways to look at that. One is you consider forward. You should consider it's a row vectors and go to end with which row vectors. Or you can look at the column vector and which it look like that. Okay. But in this particular case, this view actually it's a simple one. It's a simple one. It's basically tell you how you go from this rotation measure and where it ends up. Okay, where it ends up. So here we basically choose this three, put it in here, but consider it's a row vector, and going through this rotation and end up with where it will be. So suppose you put X here, you come to XC. You put Y here, you come to YC. You put Z here, you get ZC through this rotation matrix. Okay, and that's like the change of coordinates. So you need to sort of convince you this is the right formula to go, okay, rather than you put the 1, 0, 0 here, okay. It's not this way, it should be this way. Then the R is easy to get because X0, 0, base X0, you put 1, 0 here, you are reading what? You are reading the first row of R. Okay? You put X times this, give you the first row. Y times this, give you the second row. And Z times this, give you the third row. So that's basically explain this one. Okay, operator, can you switch back to the computer screen? So this equation base says, if I use the row vector, this guy, not the transpose, okay, just a row vector, times this one, so X should come to this guy, Y should come to this guy, I want to align them, Z should come to this guy, or I want to align all the three. Then if I put a row vector 1, 0, 0, I should get this guy out. Let's forget the rotation, or the translation, just focus on this part. So if I have 1, 0, 0 in, I will read this guy out. The other will be 0, right? And this will be exactly happen to be this vector. And then second one, I put a 0, 1, 0, this one input. So it's a 0, 1, 0 for the Y, and you will read out this guy, and that gives you the second column. And then Z is 0, 0, 1 here, and 0, 1, 0, 0, 1 times this part, you will read this one, and this one will be just happen to be the ZC. Okay, so suppose there's no translation, just purely rotation. And this 3x3 matrix actually is the projection of, I say this three vectors will rotation and then eventually align with these three vectors. And going this way, you get that. Okay? So if you have any doubt, you can try some small examples. Put this R equals 0, and just try to some small, and then you can relate these two just through this matrix. I think that the best way, if you cannot convince yourself, just show some small examples. They always work. You're convinced, right? So anyway, you just assume R equals 0 and small rotation or whatever, and see whether really like this, okay? So any question about this? So this R/T matrix, T is the translation part, and R is the rotation part. And actually, you can write down them very easily by you know what's the camera, what's the eventually their final orientation. Okay, so now that's the general one. For this particular example, now we come to this. For this particular example, there is image plane. So I can define the camera coordinates, XC, YC, and ZC, okay, for this camera coordinate. So I given that to you. I give that to you. So ZC is this direction. You look at the negative direction, and this square root 3 just normalization, so that is a unit vector. XC is this, YC is this, okay? So these are all unit vector, and you can check the orientation is correct. I mean, XY, you go to the Z direction using the right-hand rule. So you can check the determinant. So X, Y, Z, put 3 by 3, right, and take the determinant. It should be positive 1. If the wrong direction, you'll get a negative 1. So there are two orientation, X, Y, Z. So first, they are orthogonal. You have to check. They are orthogonal to each one. Okay, they are orthogonal to each one, and they are unit. And then finally, you check the determinant and see whether it's positive 1 or negative 1. Positive 1 means the correct right-hand rule. So these are given. If there is any mistake, I take a responsibility. Actually, I derive all this myself. Okay. So I take full responsibility if there is any error here. So anyway, I give you this to you so that can you find this easily? And what's the R? R in this example is the focal length, or R is here actually. R, you need to know the image plane. Okay, so you found here to this location. Okay. So you need to find the R, and then you find actually R is 555. Yeah, that's the origin, right? That's the camera location. That's a camera location. So the center of camera is 555, and then there is a cube here. So you want to see the cube, okay? You want to see the cube. And F, I also give the value to you. Actually, F is given to square root of 3. Okay? So there's a F value and so on. Okay, so anyway, you can construct the first one is RT matrix, R/T matrix. So any question about this? Yes? No, I think that's easier. You see the two-stage, the structure, the problem structure is easier for you to understand. You put everything together, it's just you don't even know how to derive. This is a decomposition stage. You find R. This is a translation needed, right? That's a translation. Your camera move from this to here. You need to take care of the translation, right? And you need to take care of the orientation. So we simplify. We make the translation back coincide the origin, and then also coincide the 3 axes. Then we can talk about the second matrix related to the perspective projection. So intrinsic one just try to align the coordinate, align the origin. That's it. That's all we try to do. And actually, that's something you already had, 2D case. But you don't have the 3D case. But I try to explain the 3D case. Okay? So this is the R/T. R is rotation, T is the translation. Okay? So totally it's a 3 by 4. Okay? Now the second part is called intrinsic camera matrix. And this is from the camera coordinate to the image plane coordinates. So there is something we need to take care about the perspective projection. Okay, it's really perspective projection. So it looks like the following. And here, this geometry, it's similar to the textbook material. Okay, textbook material. But here we use the following geometry because this is also very, it's simple to see. So it's like here, okay? So this is the image plane. And we align the X and Y. So we consider, suppose this is X or Y, doesn't matter. And this is Z. So Z is a line, but you can consider this just like a plane. You can draw a plane. Suppose this is X, this is Y. You can draw a plane, and so on. But let's just consider Z and this either X or Y. Okay, doesn't really matter. So this is I think it's a little bit okay. So that's a point already goes through the camera coordinates. That's in the first starting from the X, Y, capital X, capital Y, capital Z, right? After you go, then you start to get the X sub C, Y sub C, Z sub C. After the external mapping. So now it's aligned and so on. So this has become the new point here. It's still in the 3D space, but with respect to this guy, XC, YC, ZC, right? The first step. Now I need to project to this point. So I need to find where it is, okay? And so you are passing through the focal point and come out to form images on the image plane. Here I show two image planes. One is a normalized one is a general one. The normalized one, basically F is equal 1. So focal length is equal 1, we call normalized one. And so in that spatial case, this term, F times this, F equal 1, it's just this value, and it's just that value. Okay, so this is a multiplication. So F equal 1 is a normalized case, but generally F may not equal 1, and we can look at general case. So if F becomes bigger, you are able to get a bigger images, right? And if F is smaller, you get a smaller image size. Okay, so it depends on where the F value is, and that's the focal point. Okay, that's the focal point, and then the object can be far and so on. So any question about this diagram? Okay, so this point is after alignment, and then this is through the Pacific projection. So point will come here. F play a role. So I want to say is F play a role. So there is basically there are two things you need to think about. So one is about the matrix. So we look at this matrix. So it's a XC, YC through the K, and this omega basically try to explain the scaling effect. There is a F scaling effect. So we can write down this matrix like this one, and the scaling actually relate to the ZC. Okay, so omega just like ZC. So we still don't know what's the scaling. We put the omega here, and this part, the first one is related to the triangle relationship, and the second one related to the translation effect. So the triangle effect basically is this triangle and this triangle. So how you find the ratio between this, say, XC and this one? Basically, the ratio is this divided by this, right? It's a triangle, similar triangle. So ZC divided by F will be equal XC divided by the projected value. Say we can call it a small x. So let me write down. So operator, can you show my notepad? So we have a similar triangle. So we have the small x divided by F. It's like the XC divided by ZC. So X is just F XC divided by ZC. And similarly for Y. And so Y is F YC divided by ZC. So you write down this, and then you check the figure. So operator, can you switch back? Switch back computer screen. Switch back to computer screen. Yeah. So that's what exactly I say. I have small x here or small y here. Small x divided by f is equal capital XC divided by ZC. This is a similar triangle. And similar small y divided by f is a YC divided by ZC. And so that's exactly what I write here. Okay? Right? So that's about the distance. And if you choose f equal 1, this term to be just here. So that's a normalized. Okay? So that's what basically we say here. There is a scaling. Scaling is if everyone divide by, because W, in this case, omega is equal to ZC, right? Because omega times 1 equal 1 times ZC. So omega is ZC. So then this is just Fx divided by omega. So it's just divided by ZC and divided by ZC. So this is exactly what we have before. Okay. Finally, the translation. Why we needed the translation? Because the thing is, Cx and Cy, I think it's the image plane. It's not, there is a difference between the image plane center and the focal point. Okay. In the previous case, we used this focal point as the main thing, but actually we use this focal plane as the origin and consider their relationship. But this guy needs to go to the origin, it has to be aligned. So there is a Cx, Cy relationship in the Z direction. So Cx, Cy is equal like let me see. Okay. It's a translation. Oh, sorry. Okay, so what I want to say is we use the origin here, but when you have the image, you have to consider the image origin. The image origin actually is not the center of the image. The image origin is the upper left corner. Okay, so that's the translation. So finally, you need a Cx, Cy translation is needed. Operator, can you show my notepad? Because when we say the images, we use this as the image center. But when you talk about image origin, actually, how to say, if you really want everything, just Cartesian coordinate, image origin is here. Suppose let's stay with the Cartesian coordinate. We are not going to the image coordinate, just Cartesian coordinate, okay? The Cartesian coordinate, the image origin is here, but the derivation we just showed, we showed the origin is here. So there is the Cx, Cy here. There's a translation effect. Is that clear? So there's a Cx. So Cx, Cy actually is 1/2 of the image height and 1/2 of the image width. Here we all consider it's everything respect to the unit vector in the 3D coordinates. Okay, so we are not going to talk about any image pixels. Everything is the 3D vector x, y, z, and their multiple. Their multiple. Say c times x means c unit of x. C. Do you know what I mean? Everything is the space. No image pixel yet. So everything just talk about the consider x, y, z as a unit vector and how much amount of that. Okay. So here it's the images, but when we derive, we assume the origin here. But actually, when we look at the image, Cartesian coordinate origin is here. So then we need to translate back. Okay. So there's a relationship between these two. So the origin should be here. Okay, the Cartesian coordinate. Okay, so that's CXY is the image coordinate of the intersecting Operator, can you show back the computer screen? So CXCY actually is the coordinates of the intersecting point between the optical axis and the image plane. So basically, it's the center of the image plane. So this is called the optical axis. And you intersect with the image plane either here or here. This is normalized one. This is the general one, and that's the intersection. This is called the optical axis. Means it's going through the focal point straight in a straightforward way. Okay, just no angle here, just straight, and it's intersect. That location we call the CXCY. Okay, and so you need to translate that and so on. And usually it's 1/2 of the image width and 1/2 of the image height. Okay. So any question about this? And this is about Cartesian coordinate. And later on, you already learned how to convert the Cartesian coordinate with the image coordinate, right? That's the first part of the lectures. So now everything can be tied together. Okay? So it's really not very difficult to understand in concept, but of course, you need to be careful to work out the details. Okay, but if you think about this, it's much easier than building like a microprocessor, right? It's so complicated. There are so many things. Building an airplane is very complicated. This one, still life is still easier. Just spending on a piece of paper and maybe 1 hour you can get everything straight. Okay, so just be careful. But I think I want to show is the building blocks. A lot of complicated things, really, it's a small building blocks. And then you have small building blocks. Gradually, you can build a big system. And this is camera image model is very commonly used in all the computer graphic animation. So it's not something very big deal, but you just need to get familiar with. Okay, so any question about this? High level, I think you know, but then detail, you need to go through the math and so on. Okay, so let me go over the homework for the part A, part B, part C. Okay, so part A, basic part. So figure A show the 20 by 20 images. So there are 5 images. Funny, E569. Usually that's not a good term. Okay? When you say something is funny, it doesn't mean a good thing. So fun is a good thing. So E569 is fun. That's good. E569 is funny. That's not good. But I think for foreign students may not be very sensitive to this kind of term. That funny and fun is all the same. But if you are in US long enough, you know fun is a good thing. Funny is not a good thing. But anyway, I didn't pick this. Maybe 569 indeed not fun but funny. Can you see the difference? So E569 is not fun but funny. Okay, so that means it's a negative comment. It's really just it's a very poor job. But anyway. So, okay, I accept that criticism. Another one is Tommy Trojan, the logo. Another one is football player. Another Trojan, this must be the USC fan, right? Everything about USC. This is just one thing, the Dodger. Okay. So anyway, so we put this one into this surface, put this one in the surface 2, image 2 to the surface 2. Image 3, put the surface 3. Image 4, put it here. 5 here. 6, there's no images because 6 eventually is the bottom. You can put something there, your photo, but no one will see it anyway. You can put whatever you like, okay? So anyway, you can put things on the surface. And so basically, you needed to consider how to relate the image pixels and the 3D world coordinates, right? So then you need to consider the pixel, how much the pixel occupy. What's the size of the pixel? Okay, so then there is talk about this. So there are 20 by 20, so there are 40,000 pixels, right? And each size 200. But then there is a surface. The surface is actually there are 6 surfaces is put here. So surface 1 is the top one. So and it's formed by this side. Each side is a unit like 2. So for this side, x from -1 to -1 to 1. This is x. X is -1 to 1. And yz is equal 1, 1. Okay, so this is the one side, and this is another side, y from the -1 to 1. And this is another side, and this is another. Sorry, this is sort of 4 boundaries, and this is surface. Okay, so surface z equal 1. Remember, look at that, z equal 1, 1, 1, z 1. But 4 corner, this 4 corner is x, y, 4 corner. Okay, so this is surface 1. This is surface 2. Surface 2, x is constant. X is 1, 1, 1, 1. X is constant. Surface 3, y is constant. 1, 1, 1, 1. Right? So this is all constant x, constant y, constant z, different surface. 1, 2, 3. There's 4 and 5 in the back and 6 in the bottom. Okay, so this is a cube. Imagine that. And basically, we consider this unit like 2 units, right? From -1 to +1, there are 2 units in the 3D coordinate. And I assign 200 pixels uniformly. So that means each pixel like a 1% unit. You know what I mean? There's a unit, but each unit has 100 pixels. Each unit has 100 pixels. Another unit 100 pixels. Uniform distributed. So you uniform distributed 200 pixels along these 2 units, and 200 pixels along 2 units, and so on. So now I relate the pixel to the coordinates. Okay. So will be played on the 5 surfaces in figure AF. You can ignore the bottom face in this problem. With the configuration in figure 5, the camera can observe image on face number 1, 2, 3, because the camera is in the 5, 5, 5 position. So look at that, only see the 3 surfaces, three faces, right? And write a program to generate location intensity information of the 5 images by assuming the unit length of the world coordinate is 0.01. So the unit length of the image pixels, basically. Okay, so that's about the unit pixels. So there are 200 pixels along the one direction divided by 2. So it's 0.01 per pixel. 0.01 unit length per pixel. Okay, so unit length. And then, so what you need to do is that you need to identify. Originally, it's a 3D space. There's no pixel value. There's no gray label, no color. But now some of them, now you start have, not some of them. You can say all the surface, you have assigned a pixel value, color pixel value to it. So you have some color. At least for those 5 surfaces, you have color. You know what I mean? So each point, 0.1 unit square, so 0.1 unit, that's like 0.0001 unit square. That square has a color associated with that. So I just want you to be able to associate with each location, geometry location, with either gray label or just color. In this case, it's just color. Okay? So there's RGB as a function of the space. Is that clear? So it's originally the 2D images, but now the 2D image moved to the 3D coordinates and associated with the 3D coordinates. And if you want to, I think I would suggest is you allow the TA to write a subroutine, okay, and let TA input some values, and you can see the corresponding.
The time is 1 o'clock.
As an output, because the TA is very hard to see everything. Okay, I don't want you to print out everything, every coordinate, every color. That's too much. So I want like a TA can choose some point. She or she like to see, and just input that coordinate, and you show the color. Otherwise, how do I know you do a correct job or not, right? So it's a random selection some point, and the grader will random selection some point, and then you need to generate that point. So the program will, once you give a point, of course, it's in these 5 surfaces, okay, will not give it to something. Or maybe give something outside, then you can say they're not defined. There is no color defined, right? But once it's inside the 5 surface, you have to generate 1 color for that. Can you do that? Just RGB for that location. So that's a way to test whether your program works or not. Okay? Okay, so I think Hyun-Soo, explain clearly in the DEN website, say what's the input-output. The input-output is the location in the 3D space. But if it's on the surface, we have defined the color, the student should show the corresponding color, RGB. And if there is no definition, then students say just not available. Okay, so outside the 5 surfaces, then it may be in the air, right? In the interior region or exterior region or interior region, then you say not defined. Okay, so then I can check whether you really do the job or not. That's about pre-processing. The second one, capture the 3D scene, advanced 20%. So in this part, you need to display the cube images on the image plane captured by the camera. By following the aforementioned step, you can determine K. This is the intrinsic camera model, and then R, rotation /T. This matrix, it's a extrinsic camera model. Please first implement the forward mapping algorithm. Forward mapping basically tries to do is what I said. It's a row vector, and through that K, RT and K, get another row vector. Okay. But the result will not be good because the reason is you are not able to go to the point you want, integer point. Sometimes you go to fractional point. So it's a little bit messy. But I think the main reason for that is the TA was concerned there's another issues, okay? So I need to explain this a little bit. It's doable, but quality may not be very good. So you can do truncation, you can do whatever, okay? But let me explain the motivation of this problem because I emphasize a lot. Never do forward. Then why the homework asks us to do the forward? Because there's another complication, okay? So the 3D, the camera model, operator, can you show my notepad? There is a problem is in the real world situation, there may be, say, camera is here, so there's a camera. There may be multiple objects, okay? And when you try to look at the things, actually, you may see multiple points. Okay, so if you want to do the reverse mapping, so you should do the reverse. Reverse mapping, actually, you will not see only one point. You can see all the points in the middle. Okay, so there are multiple values, but forward, you only have one. Right? Forward, you just project to one, but unless you go to different part. Okay? So there is another problem I didn't cover in this homework, but it's important. It's so-called the depth cube. So you have to compute how many, or depth buffer. So there is a projected point, but when you trace back, actually there are sometimes multiple objects. And so you have to store those multiple objects in the depth buffer. And then eventually select the one with the smallest depth buffer. Okay, so there are different depths. So suppose depth 1, depth 2, depth 3, depth 4. And which one you really can see is the one with the smallest depth buffer. And in this case, actually, sometimes you may have two points, right? In this particular example, we have, operate, can you show the computer screen? You show the computer screen? if you consider the light going through this, the light may come from here or here. Okay? The light may passing through 2 planes. Okay, so you may passing this plane and this plane or this plane or that. You may come multiple planes. And you need some way to determine actually this plane is closer to the camera. You can see. The other plane is far away and you've been occluded. You cannot see. And sometimes they even talk about transparent. So it means the closer one, but it's a semi-transparent. You can see something in the back because that one is not totally opaque. Opaque means it's just no transparency, right? So it's a little bit tricky. So the TA sort of consider it, say, well, why not just do forward? There's no depth buffer and so on. So that's the reason. But I still feel we need to do the reverse. Okay. But anyway, I think I say there is also another thing you can discuss is about the F. Because if you adjust F, make it smaller, even smaller than 1, then the same thing come to here, actually you are able to get a denser output. So once the denser output, then sometimes the round-off error will become smaller and smaller, right? If you have something very far away, F is very large, then you will have a lot of missing hole, and the round-off will be very severe. The distortion will be big. But if you have smaller F, actually the round-off effect may not be very, very obvious. Okay, so you can make things, you can adjust things. But again, what I want to say is forward mapping is not tradition. Forward mapping usually is not the right way to do. But here, just ask you to do so that you can see the distortion and so on. Okay. So first implement the forward mapping. Forward mapping means starting the surface. You're starting all the surfaces you have, surfaces 1, 2, 3, and then go to the camera images, and then see how it's formed. But you will not be in the integer positions, right? You will not be in the integer position. I think I can suggest several ways to do things. If you don't go to the integer positions, maybe you have to see. One is round-off, but round-off is also not good. So I will suggest the following. Suppose you have the forward. So there is 3 surfaces. Operator, can you show my notepad? So suppose there are 3 surfaces, and then you go to the image plane, and the image plane, the pixels, you may not be able to go to this integer position. You make something in the middle, right? But then I think you can consider it's you look at consider a small window for that, and doing some kind of Gaussian filtering, or you try to weight them but normalize them. So eventually you see what inside. You try to do the averaging of this input and so on, and then eventually move to here. Is that clear? You round off, just directly round off to here may be not very good, but you can consider if there are sometimes multiple things close, or you can consider a little bit larger window or something. Do a little bit smart things, and maybe you can make the distortion smaller. Okay, let me say again, because I saw a lot of confusion surfaces, confusion faces. Suppose there's a coordinate here. The coordinates map to another coordinate here. So I have to copy the RGB to this point, but this point I cannot display, right? I only can display here. I cannot display here, right? So, but I think I can consider this point is like a averaging of surrounding pixels. Averaging of surrounding pixels. So I can say, well, how many this point come to my neighborhood? It come to my neighborhood, it close to me, then I will not just use 1. I use surrounding, there may be multiple close to me, right? There are multiple close to me. And then this one I say, what's your color? What's your color? What's your color? Right? And then I try to average the color. I give a weighted average. Is that clear? So first, it's just point-to-point correspondence. But anyway, you only can show, dot. But the dot, it's also a pixel. Pixel means still a region, right? When we say something a pixel, remember we do the Gaussian coordinate. Gaussian coordinate, everything can be fractional. But when we say a pixel, pixel means it's a region. Do you remember the early day when we talk about the yeah, I think that this is before that. So when we say a pixel, actually pixel integer, but actually it still covers a lot of fractional points in the 3D, 2D. Anyway, it's really a continuous domain. You know what I mean? Integer pixel still can cover a lot of continuous domain indices. It just covers a region. It's not just the itself. So it's cover a region. So if we can have a lot of pixels going through a neighborhood, we are able to find their corresponding color, and then sort of try to do a little bit averaging, or you can do the median filter, find the median value. Sometimes averaging is okay, or sometimes you do the median filter, it's also okay. Mean or median, all okay. Then you can process that. Is that clear? So that's some way you can handle that forward. And then you can discuss the distortion, so how you look at that image result. Okay? So that's one way, and we can avoid a depth buffer problem if you do the forward. So we just search the surface. Actually, it's a little bit cheating because we basically know which one is the closest camera. How do you know camera 6 not closer to 1? Because camera 6 the bottom, 1 is, you can see. But that you use human knowledge, right? So you just look at those visible surfaces going back to the camera. But the more natural way to do is to do the reverse the mapping. Okay, so here, let me continue the homework. Operator, can you let me just finish the homework? Computer screen. Okay, so you need to display the cube image on the image plane captured by the camera by following the aforementioned step. Okay, then first implement the forward mapping algorithm, and using focal length, this image is 200 pixels and 200 pixels. There is one more parameter called the pixel density. Okay, so there is the pixel density on the surface, but this pixel density is on the camera plane, image plane. These two pixel densities are different. Okay, so we still can define the pixel density. So the number of pixels per unit length in the camera on the image plane. Okay, and a poor choice of pixel density will result a project image either too small or too big. So suppose the pixel density is too large. So then you will use the 200 pixel in a very small region. Okay, in very small region. So the image will be very small. If pixel density is very large, very small, then you can have something very, very big, and it's very distorted. So you can choose a certain pixel density, specify a good value of pixel density, and provide the reason for your choice, and discuss the resulting projected images. If there are undesirable artifacts, explain the source of the distortion. Is there any way to improve this? If so, provide your own algorithm. Okay, so that's the forward. Then with the set of parameters obtained above, please implement the reverse mapping from the camera coordinate to the world coordinate. What are the challenging reverse mapping? I think, why not, I think let's have a break and we'll come back to finish that. The first problem is, no, I think that's, don't use the second order. Second order makes things just complicated. It will not give you the effective problem. No, I think that if there is no, it's sometimes experience, but for this kind of things, it should be sort of relatively easy if you do the decomposition.
The transformation parameters, like the square
Okay, let's come back. So there is a typo in the homework. So in the intrinsic model, we have a ZC, XC, YC, ZC. And the origin of this XC, YC, ZC is here. Because this is a point, you have ZC, say ZC equals 0, and so on, right? So this one is the origin of the, should be the origin of the previous derivation. So that you started this is the origin, then you can do the triangle, similar triangle derivation. So what I want to say is, if you go back to previous example, this point should be 555. Okay, so don't worry about the value here. The value you first worry the focal point, the place you should align first. So it's not here, it's this guy. So when you do XC, YC, ZC alignment, it's this point you want to align. Not here, it's this one. And why? Because you need that one to be the center for the next derivation. Right? The next derivation, if you center here, the origin here, you derive this extrinsic model, then when you do the intrinsic model, you are here. That's the ZC starting from this guy and so on, F starting this. So otherwise it doesn't match, right? This is not origin. This is really the previous origin. And once you start here, you do the things, and then eventually you derive X, Y, Z is not important. Z eventually disappear. ZC just the depths, but when you look at X, Y, there's no ZC. So X, Y just becomes something like that. So eventually small x, small y, ZC just a scaling, okay? So you can look at the F effect and so on. So you don't have to worry about the origin. It shouldn't be here. Origin should be here in the extrinsic model, okay? So I will ask TA to fix this problem. So we'll erase this one. Don't worry about one. And 555 come here, okay? And then that's the point you need to worry about. Okay. So in terms of the pixel density, we can see is the image size. Okay, so there is a real image size. Operator, can you show my notepad? So the image width is equal the pixel density actually times the pixel density, but this picture image width, it's a real in terms of the unit vector. In terms of the unit vector, in the space, okay. So say 1 inch, half an inch, those kind of things. Times the pixel unit becomes the pixel numbers. And basically it's a pixel, it's a width, image width in terms of the pixel number. So we can talk about image width with two units. One is in terms of the coordinate unit length. One is in terms of the pixel numbers. Okay, and they are related to the pixel density. Okay, so if you come back to the computer screen. Come back to computer screen. So this is all in the unit vector and in the space. So if you make f bigger, then the image width will be larger. Okay, and if you make f smaller, the width will be smaller. But in terms of the pixel, how many things you can see is still uncertain. It's determined by the pixel density, right? So if you choose the wrong pixel density, sometimes you may not be able to see the whole 3D surface. The cube, maybe you only see just the middle part. If the pixel density is too small, then suddenly the whole image become, the projected become too big. So you're not able to see, okay? So you really have to see about the ideal case is you adjust the pixel density so that you see the whole 3D surface or cube about, say, 80% of the images. Right? So suppose you have the square window. You have a square window, and then there is a 3D cube you see. But you don't want the 3D cube to stretch the whole image. You want to be around 80%. 80%, so you can see that 80%. And not too small, like a 10% in the middle. No one sees what's going on. Right? But you don't want it too big so that you only see partial surface. So you want to choose some kind of good pixel density so that you can see the reasonable size of the images. Okay. Everything sort of within the viewing camera window. Okay, and in terms of reverse mapping, so there is a thing here. That when you do the reverse mapping, you have to go from the first is JK. You first go from JK, that's the image coordinate, and from JK to XY, right? First from JK to XY. Once from XY, you have to go to XC, YC, ZC. So how you invert that? So that's a challenging, right? Because the only two, but now you have the three. But this three is really not the final equation, okay? So you have some constraint. So when you, starting from the pixel here, and then you go through this formula and try to, coming back to find, and you need to solve the equation to solve the intersection. Here's x, y, z, but you have to solve the intersection. So what's the intersection point here? And this 3D surface actually is very easy for your case, because this is z equal 1, this is y equal 1, this is x equal 1. So basically you have an equation. If you consider argument systems, you have one more equation, and that one more equation is, you can argument with this guy. So let me show you how the argument you can do, right? You just say you have the, I think probably the easiest way is to try to first find so you can add the constraint is like x equal 1, or y equal 1, or z equal 1 in a third equation. Okay, third equation. So the equation you can add is you can add 1, 0, 0, 0. So then let's take out this first. Okay, that's a 1, 0, 0, 0 means x, and equal here you just can put some constant here. Okay, and omega actually you can find from the z already. So you are able to get one more equations. And then find it's equal, say, equal 1. So give x equal 1, or you can have another one is 0, 1, 0, 0, y equal 1, or z equal 1. So you add one more constraint, and this constraint basically is talking about this surface or this surface or this surface. Okay? So when you see from camera, see the cube, you have three parts. One is surface 1, one is surface 2, one is surface 3. And each part, you know where it's from, right? It's some from is x equal 1, one is from y equal 1, some from z equal 1. So that's a condition so that you don't have three variables to get. You only have you only can determine really 2 variables because another is determined. So you from 2 variables to 2 variables. Is that clear? The 2 variable here, is the image XY, but you only have to determine 2 of them because the other will be determined by the surface. So you're able to go back to see where they are located in these 2 surfaces. Say Z equal 1, okay, capital Z equal 1, then you find the capital X, capital Y only. Then you find what's the color, and then take color back. So this is reverse mapping is very simple. Basically, you have solving the equation, but this equation is happens to be very simple equation because it's shooting just only that 3 surfaces. Okay? So any question about this? Actually, this is the easy part. There's a difficult part, rotating matrix, rotating cube. Let's start rotating. The world is not so easy. So you need to put another equation rotating related to this all surface change, right? So constraint change. This surface is still okay. This surface does Z equal 1. But the other surface is not Y equal 1, X 1. It becomes something else. Once you rotate a cube, then you start to see this surface and this surface become a line. Like X plus BY equals something. It becomes a line. So these 2 surfaces, there's a constraint in X, Y, but they are the line constraint. But here, so Z equal 1. So that's the bonus problems. I see a lot of students enjoy the bonus problem and almost get a full score. So now I make bonus more and more difficult to get. So that's reserved for excellent students. Okay? So some students are just so good. And no matter how challenging problem I put, they always get a high bonus point, like a 9 or 10. So now I will see how many students get this 10. So now the cube rotates along the z-axis with the anti-clock direction, like shown in figure 5, anti-clock. We capture the cube when the rotation angle equals theta, theta equals 1 degree, 2 degree, 3 degree, gradually rotate. So it's every moment rotate by 1 degree. Please make a video clip that consists of this 90 frame, 90 images. To do this, you need to use the rotational transform with respect to the z-axis. So z is still 1, z prime always z, the same, but xy, z, xy will be something like that, is the rotation equation. And then you have to solve the equation from do the reverse mapping from the image to the surface and find the corresponding coordinates, and then find its color, right? First you find the coordinate and find the color. In this course, in this part of the course, it's all about coordinate transformation, Color is eventually, how do you know you do the correct coordinate transformation? You find the right color. I use the right color to check whether you know the coordinate transformation. You know what I mean? Color is just a check. I don't do any color problem. I just find, if you do the correct coordinate transformation, you pick the right color. If you do the wrong coordinate, you pick the wrong color. So color is a check, whether you know how to do. But everything is about coordinate transformation. Change this coordinate to that coordinate, where you're here and where you are there. Just find the mapping. The whole thing about the geometric modification is about coordinate transformation. But if you can do all this, I mean, you are pretty much advanced in this coordinate transformation world. Okay? And it may look difficult, but anyway, if you go to computer graphics, this is like very elementary stuff. If you cannot do this, what you can show? Nothing you can show, right? You cannot show anything. So this is really a very fundamental thing in computer graphics. Okay? So I know your pressure, okay? So I think after this lecture, you will go home and start to work, I believe. Otherwise, you don't know whether you can finish the job, right? Okay, so now we go to the textures. Okay, so let me first explain the textures a little bit. So these are called the texture patterns. Okay, this come from different material. So this I believe is like water, and there sometimes it's like raffia, some kind of textile, and this like maybe some, I'm not sure where it's from, maybe bark, the tree, the surface of the tree, and this is like grass. So human can cluster them well. Human will say this become one cluster, 3, 5, 11, right? And 1, 4, 6, another class. And 7, 8, 10 is another class. And 2, 9, 12 is a class, right? Agree? But how let computer do this? How computer cluster things together? It's very, very challenging. Actually, this is a very early, one of the very early challenging problems in image processing. It's starting from like the 60s. And why you have a lot of texture images? Because it relate to the airborne photos. So you have airplane flying through the region. You take a lot of photos of the ground. And if you see from the airplane, everything is textures. CT form some textures, you know, and different kind of forest, different tree form different textures. Desert, another texture. Lake is another texture. So all different kind of things from the sky, all texture-like. And they need to do this kind of Earth resource finding which part is say cornfield, which part is the forest, which part is the city, which part is urban, and so on. You need to do texture segmentation and so on. So that's the motivation of this. And actually, people struggle for a long time, couldn't find a good one. Okay, and in the textbook, it has some history about the texture here, texture there, a lot of old stuff. But I don't have time to go through the history, okay, because a lot of bad ideas. I would say just forget those kind of things. The textbook actually has a lot of historical things, but I just zoom into the right path, okay, zoom into the right angle, and then today there is some kind of common consensus what's the right way to do textures. So I will just teach you the right one. So the one is about classification, and clustering is different. Classification basically says I trained different image already. Say there is the water, the grass. I all train and supervise train. And then I give you the texture X. I say which one this belong to. Does it belong to this water or belong to the grass or belong to what? That's called classification. So it means already you have certain classes. I just ask you to decide which one to go. So you can do the so-called supervised training and then classification. But this problem in particular is called the clustering problem is unsupervised. It means I don't tell you anything. You just have to put the same thing together. Okay, so this is called a clustering problem. It's not a classification problem. Classification problem means already clustered. You just find this X to which one it belongs to, the classification. But clustering is you put things together, so it's called unsupervised training. It's a little bit harder than the supervised one. Okay, so a little bit harder. So this one I will talk. Then another thing I will talk is this guy. So what's this? This is called textual mosaic. Mosaic, you know, you put many things together. And so actually there are a different texture here. So there are curved boundaries. Human eye check that very quickly, right? Can you see all this and all this and all this? So human eye takes less than 1 second, immediately find all the boundaries. Please ask computer to do it. Oh, computer is just so bad. It's even worse than a 1-year-old kid. Computer will have a hard time to do this, texture segmentation. But of course, that's not the end of the world, okay? We have teach computer smarter and smarter and smarter. One day computer can see this just like a human being. I don't know when, okay? But my dream is to say within 10 to 20 years, we need to ask computer to do things almost like human. Is that possible? Well, that's a big dream. That's sort of my last ambition in my career. If I can do this, I will be very happy. I can die happily. But if I cannot do this, then I will be very unsatisfied. I say all the achievement just junk, really. I made no achievement in my life. So I cannot solve this simple problem, right? You know, I think usually people have low standard. Low standard in the sense that they say, well, they just, people do 20%, or people do say 50% accuracy. And I do 55, I'm so happy. But nothing solves the real world problem. I have to say, honestly speaking, computer vision, it's been a field study for more than 40, 50 years. But today, nothing can be really practically, nothing. It can be used under very specified environment, very controlled environment, maybe okay, I recognize a person face, yeah. If under very uniform lighting, everything very good and so on, ideal case, no head, no mask, no glass, everything ideal, then you can recognize the face. Compared to human being, human can see so many things, right? Can see the face. I don't need something very ideal, right? So today, if you look at the internet, if you look at the text search, text mining, internet is so good. Google, you just admire how Google engineer can do all the text search, find the right relevant topic. Second, speech. Speech now, we have small smartphone. We can ask the question, and then can translate, put it in English, and then search. And what's the accuracy? Accuracy is very high, right? You try the smartphone. I think, of course, sometimes you may not be very good because your English is not very. Partly the English problem, not really the software problem. You cannot be so smart to overcome a lot of change pronunciation. Okay, that's maybe one of the problems. So you have to train the phone to recognize your voice, your particular accent. But image processing, visual computer vision, it's very hard to use. Very hard to use. So I will say we're still very far from the goal, but I'm really not willing to say the situation stay the same in another 20 years. That's really a shame for all the people working in the image processing field. Okay, so it's not really about the publishing paper in the CVPR, in publishing paper in ACM multimedia. Okay, I think that's a low goal. The high goal is to make things really work. That's really the goal. Okay, so anyway, there is a lot of work to be done in this field, and I just try something, and you can see how poor the computer just can do today. Not very nice. Okay, so we will talk about the feature, texture. So it's a chapter 6. Chapter 6. Am I right? So texture analysis, we try to understand textures. So that's including classification, segmentation, clustering, all these kind of things. These are the different things. And very brief history. Let me see. There are long histories of the texture analysis. So it's a long history. But nothing worked well for almost like several decades. Until there is a interesting work by USC master students, okay? So Lowe's, 1979. So that's a USC MS student. He's not a PhD student. Okay. He wrote a paper on a way to handle textures. Actually, he wrote a paper about texture segmentation. And the paper was published in a so-so conference, not a very good conference, called SPIE conference. Okay. And I used to submit this paper to the SPIE conference. But later on, I got criticism by people say J-Core submitted paper to SPIE, which means he's not good. Okay, so I decided not to submit any paper to SPIE anymore. Just forget SPIE. You know, it's again, you know, there are a lot of problems with that conference. But sometimes I use that opportunity for student train, try to train students. But later on, I say, well, I just don't need to go there. Okay, so the paper published at SPIE conference is a very low quality conference, but the result looks pretty good. Okay, and he couldn't explain. So his paper only can be accepted there because he cannot. He did not understand why it works. So I tell many of our students, if you cannot explain, no matter how performance look, you only can go to the second tier, third tier journal or conference because there's no explanation. You don't understand what's going on. You are lucky. This kind of thing is very rare, but still happens. Okay, they are lucky people got some result without knowing why. Okay, so of course he tried hard. Okay, tried maybe day and night in lab. So in some things not lucky. In some things not lucky because he tried, but he couldn't have the capability to explain why. Okay, so his paper really very hard to find where it is, but it's about the loss filter. We call loss filter. But actually, this method stand out among the peers. And you know, because it's publishing social conference and so on, so it takes some time for people to appreciate. Okay, so later on there is a history. Let me see whether. I really. So let me give you some history. Okay, so I think it's until like 84 or 86. Around that time, people start to understand. People try to understand. So people recognize it's a powerful method. So researcher, it was recognized as a powerful method. So there is some follow-up work. Okay, so some analysis. People try to perform the analysis. Okay, and then when I joined USC, it's about 89, and I heard some PhD students from other professor students attended the qualified exam and the defense. So they are working on some kind of generalized framework. So generalized loss framework. So generalization. So then I happened to have an opportunity to see the wavelet, the birth of wavelet. Okay, so wavelet transform. So how many of you heard about wavelet transform? Most, right? Yeah, I think a Fourier transform, you should know. A wavelet transform, you should know. At least you heard about that. Okay, you may not know detail, but you know the wavelet transform is a. In that time, 87, 88, 89, wavelet transform was very, very hot. It's so hot in the sense, I joke with my student. I say, as long as you put the wavelet in your paper title, your paper will be accepted automatically. No one will challenge you. Whatever garbage you put in the paper, as long as you put a wavelet there, they will accept it. Why? Because people so curious about wavelet. They will say, how much wavelet can do for you? What's the wavelet application and so on. So, I at that time, you know, I was recommended to take a look at wavelet tools, and then so I combined the wavelet and treat this wavelet transform as a general way to do the loss filter. So basically, use this to generalize loss filter. So generalize loss filter using the wavelet transform. And the way I use the general wavelength transform is try to, because loss filter has a fixed size. It's always the same size. But I try to use the adaptive size. You know, the transform can be different size and so on. And then I had a third PhD student work on the topic, okay? And we work closely together. But, you know, there's the sad side of the story. The student, actually very good student, he passed the qualified exam, but then he was diagnosed with cancer, and actually he passed away. So he didn't have the opportunity to finish the defense. Actually, it's very sad in the sense actually he got married just within 1 year. So he married, but within 1 year he passed away. So like a lot of good things happen, but that suddenly you know, life just. So it's a lot of uncertain. Okay, so he was my third PhD student, but you know, of course I miss him a lot. And his paper, okay, so eventually we finished revision. I had another student help revision. So that paper published in Translational Image Processing. And that paper is the most highly cited paper of my work. Citation about like 1,400 right now. 1,400. It's like 1993. And so I think he will be remembered by the work. Okay, so sometimes I'm thinking the value of life, you know. So I think today probably I'm not worried too much. But today I'm more concerned is whether computer vision can be as good as human vision. That's really my major concern. That's a dream unfulfilled. Okay, but when I was a graduate student or even undergraduate student, I think, well, no, how my life can be remembered. If I will die one day. And I look at the paper with some photo, with some bio, I envy a lot. I say, oh, these people, their photo and their bio will be forever with the magazine or with whatever. So when I was an undergraduate student, I said, well, if I could publish one paper with my photo somewhere, then that would be wonderful. Right? But right now I have 200 papers, so the photo will be too much. It's not just a photo there. I really wanted something very, very good. Otherwise, photo there does not mean that to me. But the student photo indeed in that paper. And that's the only, I think maybe it's the only place people will remember him because of that publication. I think a lot of people, you know, it's a sad, but anyway, it's just gone. But I feel you have one contribution to the humankind and for his contribution. So I think his life still, I thought of him often. I don't know how about his family. Maybe his family think about him, but I also thought about him a lot because he's really a student I like a lot, but just misfortune happened. Okay. So his name is Tianhong Chen. So he definitely deserved PhD, but he didn't take the defense. Okay. And so the paper I have, actually I can show you. To do a Google search just very quickly. Just give me a moment, okay? Can you show the can you show the computer screen?
The time is 2 o'clock.
Let me see. This is, I don't know how to get that. There should be a Google Scholar page. Okay, here. So this paper is 1400, right? Published in 1993. So this is textual analysis and classification with tree structure wavelength transform. Just me and him. So this is the paper, okay? This is the paper. And Actually, I was naive. So this Lina images is not very well scanned copy. Okay, this is poorly scanned, so you cannot see. And this texture, you do the wavy transform. Actually, ordinary image, the low frequency carry more information, but texture, you have the middle frequency carry the information and so on. And so we look at the decomposition pattern, wavy transform. But the one thing I want to show you is the performance. So actually, when I was his advisor at that time, early 90s, I saw these numbers. I thought this is the regular thing. So you may not, let me zoom in a little bit. I don't know how to zoom in. So if you, can we zoom in here? So if you look at the different textures, there are 30, I think, or 20 or 30 textures. Around 30, say, 30 textures, and the classification rate is about 99.6%. To me, it's a number. At that time, I didn't know how valuable that 99.6. But later on, I realized most people do just 80 or 90. No one reached 99.6. If something wants to be usable, got to be 99.6. That's usable. So this paper went out. It immediately got attention. I heard at Purdue University, when they teach the image processing class, students being asked to implement the algorithm. I said, why? But because 99.6, the performance, in the past, before this paper, no one tried 30 textures. Because when the texture number become bigger and class become bigger, the accuracy all drop down. So people try 10, the performance already like say 90. Try 15, maybe 85. Try 20, maybe 80. Try 30, maybe 60 or 70. So no one dare try such a big database. And you try a 30, and then the performance 99.6. But of course, I appreciate later. But when I was there, I appreciate maybe just give him immediate go to the defense. No, qualify just the symbolic immediate. But at that time, I didn't know, and I didn't appreciate that's really so important. I told everyone doing 99, because I was not knowledgeable at that time. I was also young, and always had high ambitions. 99.6 doesn't mean much. I say, why not 99.9? But now I look at this bag, I say, oh, gee, at that moment, he can reach such a high accuracy with so many texture classes. It's really amazing. And that's explained later on why it's, about 1,500 citations. Because the depth, the quality of work is very, very good. Okay, so that's making me miss him even more, right? So he's really, So yeah, sometimes, a person is so good, but you didn't appreciate so much, but later on, time goes by, you realize the value. So yeah, so this paper is, I will say this paper one of the, but it's his contribution, okay? So, but I'm not going to talk much about this wavelet based. If you are interested, you can take a look at that. I want to talk about loss filter. That's you can see 569. Most cases, I'm not teaching you something very advanced. I'm teaching you something really just basic, right? But something can be go to deeper and deeper and can be, really advanced. But I'm still cover basics. I won't cover more subjects. But on the other hand, I want you to be humble. You don't think that you finish 569, you solve all the image processing problem. Of course not. You just get some basic, okay? So now let's look at the texture, like loss filter. Okay, let's come back to loss filter. Okay, so I hope some of you smart students, you may want to write one paper with a photo and bio somewhere that leave you in a different category, okay? So loss filter, let me explain how Lowe handled this, okay? So Lowe defined 3x3 and 5x5 filters. So he considered, let's start from the simpler case. So first he tried to define 3x3 filter. And this 3x3 filter is a size. And he used the two one-dimensional filter and using the tensor product, outer product, to form the 3x3 filter. So he defined three things, so-called L3. L means the local averaging. So E3 and S3. This is a one-dimensional filter. So this means local averaging. E means H. S means spot. And spot basis says this kind of shape. So this is like a 1, 2, right? So spot shape. This is the center, okay, the center. So this is like a, okay, but no, it's another direction. So same. So go plus, -2, +1. Something like that. Okay. So this is local averaging. So you are doing some kind of local averaging. The center times 2 and the 1 from left, 1 from right. Okay. So local averaging. This age, you do local age detection. This is a spot. You try to, you can view this like Laplacian, right? It's a reverse Laplacian. You can see if this is like Laplacian, right? So if you change the sign, then it's like Laplacian. Okay, so in some sense you can say this is like a zeroth order, just a smoothing. This is like a first order derivative. This is like second order derivative, and this is like a one-dimensional filter. Then you can form another dimensional filter. It's a vertical filter. So you can define L3 transpose, E3 transpose, and S3 transpose. So it means the y direction. And then you use the x direction and y direction to form so-called the tensor product. EE student may not be familiar with tensor product, but you know civil engineering, mechanical engineering, they use tensor product every day. So this is like applied mechanics. Okay, so you talk about the mechanics, physics, right? Physics, and then applied mechanics, civil engineering, aerospace engineering, mechanical engineering. They use a lot in this. Okay, so the tensor product basis says L3 and the tensor product or L3 transpose. You just form, say, 36. What's the tensor product? Tensor product means this one-dimensional vector, you multiply, you want to go to the second dimension, you use the weighting in the second dimension. But the one dimension, you go this, but this uses the second dimension. So in other words, this dimension you keep, but weighted by this. And you keep this dimension, but this weighted by 2. And it is still 1 to 1, but you weight by 1. So tensor product, basically you can generate a higher dimensional tensor form. This is a matrix form, but basically it's a tensor form. Tensor form can go to n dimension, very high dimension. But you form from the low dimension tensor, and do the inner product can form the high dimension tensor. Okay, so this is called the tensor. Vector and matrix just special case. Vector just a one-dimensional tensor. Matrix is a two-dimensional tensor. But generally, you can have an n-dimensional tensor. Okay, so this tensor product form this one, and so 1, 2, 1, 2, 4, 2, 1, 2, 1. That's a tensor. Okay, and so there are 3 choices here, 3 choices here. So totally, you have 9 choices. So this will be the 9 Lowe's filters. And Lowe just apply these 9 filters to each pixels. Okay, so he applied this to each pixels. And he used this as like a property of a local region. So he tried to understand, there's a pixel, but pixel is too small, right? You can look at local, it's 3 by 3 window, and then using this 9 characters to describe the property occurring to the neighborhood of that pixels. Okay, and this applies to every pixel. So every pixel has a corresponding 9 9 features. So horizontal may be H, vertical may be Laplacian, horizontal may be averaging, and vertical Laplacian. You have different choices, right? So horizontal, vertical choices, each one has 3 choices. So 9 choices form that. So each position has 9 values, right? And to describe that. And then they try to see the similarity. If they are similar, then they should group together. If they are different, then you can segment, you can separate them. Okay, so these consider features. So apply this 9 low filter, you can generate 9 features for every point. Okay, so I think that's the basic idea. Now the question is, why? That's what Lowe's didn't do. Lowe just say, if you do this, you get good results, and just show the final result. And so he didn't get really much respect, I have to say. You know, maybe we still mention his name. The other people may just skip his work. Okay. So why it works? I think one problem with Lowe is that he didn't take the 483. He didn't take DSP. If he had taken the DSP, the first several lectures, he immediately find the frequency domain frequency response of these 3 filters, and immediately understand there are 3 filters. One is a low pass filter, one is a band pass filter, one is a high pass filter. So these 3 implement exactly low pass, band pass, and high pass filter. That's it. So you divided the frequency in 3 bands, Y and X. So totally you divide the whole spectrum into 9 bands, X3 low, middle, high, Y low, middle, high. In total you have 9 filter bands. That's it. Nothing more than that. But he didn't explain that. So he missed the great opportunity to become famous. He just got the space domain, and in his thinking, just everything space domain, no frequency domain. I think most other engineering department, like civil, mechanical, whatever, they know very little about frequency domain. It's the EE students extremely good about frequency domain. Everything we think about frequency, right? But Lowe didn't do that. I don't know why. Lowe missed something big. He didn't use the frequency domain analysis. Just use spatial. Okay? So I think that's his problem. So do you want to try to do the Fourier analysis yourself? Can you try? How many have you or is taking the 483 now? It's almost everyone, right? Okay. So you should be able to do it. Okay, you should be able to do it. So let me just say roughly what it should look like. So L3, okay, I let you to decide. L3 is corresponding low pass filter. E3 corresponding band pass filter. Of course, not a very good filter. It's a coarse filter. It's a rough. Okay. S3 corresponding high pass filter. So when you do the decomposition, basically, you know, it's rough. Okay, it's not very good. So for example, this low pass filter will look like this. It's something like that. This low pass filter. You look at frequency 0 to pi, and this band pass filter will look like this. And this high pass filter will look like this. Okay, it's symmetric. It is from minus pi to pi is symmetric. Okay, but this looks just half of it. So this is the low pass filter, this is a band pass filter, this is a high pass filter. These 3. If you do the Fourier analysis, you are able to see this frequency response. I just plot it for you. Okay, it's shaped just like that. So it's not very good, okay? Not very ideal, not very sharp, and so on, because it's only 3 points. How much you can expect? 3 points. But Lowe also tried to generate 5 points. 5 points, then you can get a 5 band, and then you can get a more different shape. So you can get 5 points So there's a 3x3 filters. Then you divide it into more like 5 bands. Okay, so each band, there are certain band for each. So in the, you do spatial domain operation, but in the frequency domain, it's like you pass certain frequency band and suppress other frequency band. So only focus on that band pass, the particular band signal. And then usually you compute the energy in that signal, in that band. So the energy in that band becomes the feature. Is that clear? So that's basically Low's idea. Low's idea basically says, you know, of course, it didn't say that. You just do this kind of local averaging, age, and spot. Okay? But actually, you are really doing a spatial domain operation, but equivalently, you filter certain frequency band, suppress other band, and purely just choosing one particular band, and then calculate the trends in that. And then for different texture, they may have different emphasis. Some texture maybe have a dominant middle band. So look at this case. Some texture maybe have a dominant band here. Some texture may be dominant band here. So you can look at the different texture energy distribution. They have different distribution and use this distribution to describe the feature of the texture. Traditionally, people only look at low frequency band, but if you do texture, low frequency band is actually not very important. Usually more important is the middle and high frequency band. So this texture, you need to look at other band and then see their distribution of the energy in this band. But you say 5 by 5, usually it's a resolution not good enough. Suppose you have 30 textures. Are you able to separate 30 textures with 9 by 9 energy band? It will be difficult, right? 5 will be better. 5 will be better, but 5 sometimes may be too fine resolution. We don't know, you know, sometimes too fine. And then a texture maybe has some fluctuation itself. And the Waverly idea basically try to consider adaptive decomposition. I try to do the decomposition according to, so suppose in the beginning, I do suppose this is the X and Y frequency, okay? So frequency in F and frequency in Y. First I divide into 4 bands, and then see which one has larger energy. And if larger energy, we do further decomposition. And then if there's still larger, I do further decomposition until I feel I no need. So then I'm able to find the energy distribution according to this adaptive resolution. And this adaptive resolution will be capture each texture energy distribution much better than fixed resolution. So in one word, that's the difference. Adaptive band decomposition, this is fixed band decomposition. Fixed band decomposition. But we call tree structure. Tree structure means it's core tree. It's called core tree. Each node has four children, so it's called core tree. Structure Waverly decomposition. So I'm able to see, given the images, I want to see which band has a stronger energy, means more things going on there. And I can zoom in and I can do further decomposition until no need, okay? And so this is very adaptive to what? Adaptive to the image type. So different image source, I have a different adaptive decomposition scheme to tailor that. So it's a adaptive resolution, not fixed resolution. So that's why I get the 99.6. It's not by luck. It's really by good reason. And of course, the paper had to explain the logic, how we think, how we handle, and so on. Okay? So this is the about the texture feature extraction. Okay, so so far so good. Any question? So now let's look at the texture. Let's start the simplest problem called the texture classification problem. So texture classification problem. So textual classification problem basically says we have a couple of textual samples. So suppose we have sand, a couple of sand samples. So sand A, sand B, and so on. Then we have some grass, for example, and then we have several samples, and we may have some kind of raffia, and so on. These are the samples. Sample A, sample B, sample C, and so on. Okay. And you can different types. So you can go to 30, you can go to 100. You know, if you have more textual types, it will be more difficult to do the good classification. Then I can pick one, say grass, but I call it texture X. So then you tell me this X go to which class? Okay, it's a sand or grass or whatever, like depending on how many. So this is called the classification problem. You have to choose one among you know. So this part you need a training. You learn the characteristic for each type, and then for this one you also get the features. You extract the features and do the feature comparison. This feature compared to the what feature in this class, and then see what's the where it belongs. So usually we have a feature space. Feature space in loss filter case is like a say 9-dimensional features, right? So generally it's a high-dimensional space. So this is a feature 1, feature 2, feature 3. Higher than 3, I don't know how to draw, but you can think, imagine in your brain, right? So suppose you have sand, and you calculate the feature. So suppose this is 9-dimensional, okay? So using the loss filter, so you can consider each one as a 1, but then each pixel you can, but it will be fluctuate a lot from sample to sample. But you maybe do averaging because this is homogeneous. So each pixel only give you a sample, and it will be statistically fluctuate. So we may consider mean of them, mean of the subband, the energy of subband 1, mean of subband 2, mean of subband. The mean usually will be more robust. So one image we may draw a point in the space. So that's become the mean of the 9 features. Vector. So 9 features define a vector, okay? And we can find the vector mean. So it's still a vector, but it's an averaging across the whole images. So each pixel has a mean, so you can call mean. Then second image, you can put another point. So this is A, this is B. And third image, you can put C. And if they are same, all come from the same, they should be close to each other. They all come from the same, and if it's good features, they should be close in the feature space. Okay, grass, you can do the same for the image A, image B, image C. You can also treat there are different samples. But then this may be grass, may be here. So this may be sand cluster, this may be grass, and this raffia may be located here. Okay, so it's all about the different distributions, but if it's a good feature, the inter-cluster variance should be big, and intra-cluster should be small. Okay, so if good features, what's the good features? It's an intra-class variance is small. An inter-class variance is large. So it means they are from different classes. They should be more separated. Okay, so inter-class variance is large. But if they belong to the same class, intra-class means the same but different sample. Intra-class variance is small. That's a good feature. And bad features is everything that mixed together, right? You cannot separate them, or everything that come together, then you don't know this X, you don't know how to decide. So now your X, you analyze this X and find its features, you do the same feature extraction, and see where it's located. It's located in this cluster, or located in this cluster, or located in this cluster, or located nowhere. So no, there's no something. Then this may be just the don't know. There's none of above. Yeah, it's possible. You may come to the texture is none of above. It's far away from everyone, right? There's none above. But if it's really from there, it should belong to this class. So the way is we control we calculate another mean of this multi-samples, another mean here, another mean here, another mean here. So this mean is a sample mean, different sample. The previous mean is about the pixel mean. There are many pixels in the images, so pixel mean. But then there are 3 samples we can consider mean, mean, and mean. Usually we call this a centroid. Centroid is the mean of multiple samples and calculate the centroid. And then if we have X coming, we just calculate the distance between this X, unknown texture, and with the different centroid you have. And then the closest, shortest distance we classify to that class. Does that make sense? That's a classification problem. And clustering problem is a different thing. Clustering problem means that I'm not going to say X. I just give you all this, I don't know. And then what you need to do, you need to pull this and then say, well, they are one group, they are one group, they are one group. You have to claim they belong to one group. And again, how you claim that? You have to use this property. Intra-class variance is small. Things in grouping. And segmentation is a little bit tricky. Segmentation, you have to look at local window and see whether they are homogeneous or they are not homogeneous. Okay. So for example, let's look at the computer screen. Segmentation, you look at this one, this region, then it seems more homogeneous, and we have to say indeed that they are all homogeneous. But you are in this window, they are half from this, and then you really don't know what it is. And these are in the transitional area, right? And similar, there are transitional area. So then you have to find out those kind of transitional regions. And then these are homogeneous, but this is not homogeneous. But texture is challenging is because it's not a smooth region. They're all the same. They are variant, they are different, but somehow they own same property. So it's not a uniform surface, it's not flat. It's some variation. But this variation somehow, globally, you look at them, they are homogeneous variation. The changing pattern is similar. So that's really make a texture very difficult. The texture has statistical property. It's not the same. But somehow people feel they are the same. So what's the things that make people feel it's the same? That's the secret. So the feature extraction is so difficult. It's because of that. So people try many ideas. But the load filter really, the mouse, there's a name for that. Usually, load code is a microstructure method. Load code the microstructure method. Because he thinks he checked the microstructure of the local neighborhood of pixel. So microstructure. So to me, what's the microstructure? Age, spot, averaging. And later on in the 5x5, there are so-called wave. There are different local structure. There are different, like called age, spot, wave, ripple. This is called local structure. Okay, so he looked at the spatial domain, he looked at like a different local structure. But I would rather call, and actually we should call it a multi-channel method. The correct name, probably too arrogant to say that, okay. The preferred name, I think of course, again, because you are not in academia long enough, all the words may mean the same thing to you, but I'm in the field long enough, I need to know politics. Whenever I say something, I have to be very careful. If it's incorrect, people will feel very upset by your offensive attitude. So preferred name then that's much more friendly, right? Is multi-channel method. Can you see the difference? Microstructure, very ill-defined, but it's basically a space domain approach. Multi-channel method is a frequency domain approach. And basically, we try to do decomposition in the frequency domain. So it's called a multi-channel method rather than microstructure method. But if you do this angle, you know how to design things, and you can generalize from fixed resolution to adaptive resolution. If you do this, how you generalize it? The story ends, right? Microstructure. How many microstructure you can think of for local pixel? Not much. You know what I mean? So looking at the angle, which angle you look at the problem, make things different. Once you understand it's a multi-channel method, immediately you think about channel resolution can be adjusted rather than 3 by 3, 5 by 5. Right? Okay, so I give you the high-level view. Originally, I want to finish this, but I feel I was too aggressive, so I would rather wait until next Friday. Okay, but you can do this. The homework actually, the easiest one is 1 and 5 and 3. Problem 1 and problem 3 are easy. Problem 2 are more challenging. So you definitely shouldn't miss the problem 3. Okay? It's straightforward. And problem 1 is also easy. Only the really challenging problem 2. So if you really need to give up something, give up problem number 2. Don't give up on problem number 3. So we'll cover problem number 3 next Friday.
This concludes EE 569 on Friday, October 18th, 2013.